Hi, my name is Wade Cook. Thank you for your interest in this virtual conference. It's a strange time we live in. Today, I'd like to spend a few minutes talking about data envelopment analysis, or DEA, from the perspective of what I shall call shared resources, common or shared resources. Slide 2. DEA was developed by Charles Cooper and Rhodes in 1978 as an optimization tool for measuring the efficiency of each member of a set of decision-making units relative to other DMUs in that set. DMUs might be bank branches, hospitals, schools, lots of examples. The conventional model shown here as Model 1 assumes that each DMUJ possesses its own quantities of a set of inputs, X, and generates, or the result of, a set of outputs, Y. Furthermore, it's assumed that the input-output bundle for any given DMU is not connected to those of the other DMUs. In more precise terms, the DMUs are assumed to be independent of one another. You'll notice on this picture that's in front of you a projection of points like E and F onto the frontier. Next slide. In some situations, there can be some form of interdependence among the DMUs. Consider a couple of examples. The sales of automobiles, such as a Subaru, are very much influenced by TV, radio, magazine, and newspaper ads. These ads are a form of common or shared input, benefiting all dealerships in the vicinity where those ads appear. Furthermore, the ads can vary from one vicinity to another. This means that the set of all dealerships can be organized into groups, whereby each dealership in a given group not only has its own dealer-specific inputs, but as well benefits from the common set of inputs or shared inputs pertinent to that group of DMUs. A second example is a measurement of efficiency of university departments. Here, each department falls within the jurisdiction of the faculty. Each department in each faculty has its own unique set of inputs and outputs, but at the same time, all departments in the faculty generally benefit from a common resource such as administrative staff provided by that faculty. In the case of administrative staff, one generally finds that they provide a service to the full set of departments within each faculty. Thus, for all practical purposes, those academic staff can be considered as department level inputs, while non-academic staff are faculty level inputs. Next slide. The idea of shared inputs and outputs is not new, of course. One type of sharing, which we can refer to as type 1, was presented by Beasley in 1995. That publication is shown here. He was the first author to examine efficiency in academic departments in a university setting, which involves sharing inputs across the two functions, research and teaching. A somewhat similar approach was suggested by Cook, Ababu, and Tunter in their 2000 and 2001 publications, which involves splitting resources across sales and service components in bank branches. In these cases, the sharing took place within a DMU, where certain inputs are split across functions or components, which can be thought of as sub-DMUs. It's important to emphasize this idea of splitting within a DMU as opposed to splitting across DMUs. A second type of shared factor, which we can call type 2, is that involving the allocation of a fixed cost or resource across the set of DMUs after the efficiencies have been determined. Two early papers in this area are shown here as Cook and Press and Cook and Zhu. Next slide. Let us suppose we wish to evaluate the efficiencies of a set of departments within a university. Consider the following input and output factors for evaluating a set of university departments. I've shown here potential inputs might be department budget, total academic staff, total non-academic staff. Outputs might consist of external research grants, total numbers of undergraduate degrees awarded, and some kind of weighted function of publications. Next slide. Consider a simple example. Let us suppose we have 6 DMUs, numbered A through F. Let's assume there is a single output O, which I've taken as 1 for all DMUs. And let us assume there are 2 inputs, X1 and X2, where X1 represents a regular input, say total academic staff, and the latter is a shared input representing non-academic staff. Figure 2 shows the inputs in a two-dimensional space, viewed from the perspective of Model 1, and the output can be ignored. Note that A, B, C, and D exhibit strong efficiency, while E and F are considered to be weakly efficient. This conventional model is deficient, however. Model 1 is deficient and it fails to properly capture the dynamics of shared inputs. Specifically, Model 1 presumes that an adjustment theta xi plus 1 j naught in a shared input when evaluating the efficiency status of j naught. The assumption in Model 1 is that it does not influence the status of other DMUs in that same faculty. But of course, this isn't true. The proper representation, however, when a shared input is present, is to view the input adjustment theta xi plus 1 j naught for any given j naught in that faculty as being accompanied by the same adjustment theta xi plus 1 j for every other j in that faculty. Thus considered for the moment Model 2. And we switch to the next slide. So notice here, we replace lambda j by lambda j theta for all departments j in a given faculty, thereby creating a nonlinearity. We happen to solve this Model 2, which I call Model 2. We happen to be solving this using treating theta as a parameter. Note that what we've done in going from Model 1 to Model 2 is we've changed one constraint. Constraint 1b has been changed to 2c. So notice here that on the left-hand side, instead of just having lambda xi plus 1 j, we instead have lambda times theta xi plus 1 j. The point is that when we wish to evaluate DMU j naught against its efficient peers, if j naught is not efficient, then the evaluation will be against only the efficient peers and DMU j naught can be ignored. If j naught is efficient, then theta equals 1, and it doesn't matter whether we use the expression lambda x or lambda theta x, you get the same thing. Next slide. While on the surface, Model 2 might appear to provide an appropriate way of dealing with the issue of shared inputs, the model may possess a potentially damaging feature. To explain, suppose we apply the model to the simple example considered above. Recall that DMUs D, E, and F under the conventional Model 1, which we designate here as a CRS model, that they are all deemed efficient. In that model, we ignore the fact that those departments are naturally interdependent. See again Figure 2. Observe, however, that when we apply Model 2, we obtain the projection shown in Figure 3. Note that DMUs E and F, which were deemed efficient earlier, are now deemed inefficient rather than efficient as they were in Model 1. Department E has an efficiency score of 0.8, and in a radial sense is projected from point E, projected to point E prime with coordinates 20 and 6.4. DMUF is on the other hand projected radially to F prime with coordinates 20 and 5.16. It has an efficiency score of 0.645. In the conventional CCR Model 1, as reflected in Figure 2, we note that any projected value of theta xij naught cannot be less than the minimum of xij's. Hence, the projection must stay inside the frontier and its extensions. Thus, the projection is guaranteed not to push through or penetrate the frontier. In the conventional DEA situation, the data characterizing any given DMU remains unaltered in the optimization process of 1. In other words, the input data xij on the left side of 1B and the output data YRJ on the left side of 1C remain fixed. Now, this is an important point because in the situation where there is a shared input present, this is not the case. Specifically, when deriving the efficiency of a given DMU J0 using Model 2, constraint 2C acts to alter the shared input data for the remaining DMUs in that faculty. Specifically, when evaluating a given DMU J0 in a faculty, xi plus 1j is replaced by theta xi plus 1j for all j in that same faculty. Given this fact, and given that we wish to ensure that projections do not pass through the frontier, we impose an additional constraint. See Model 3 in the next slide. So notice here, when we impose this additional constraint, which is constraint 3E, by the way, what it says is we don't want to push through the frontier. So the frontier will not be penetrated. And it turns out that coincidentally, we get the same picture that we had back in Figure 2. Next slide. It is worth mentioning that the whole idea of a production possibility set is quite different in this case, let's say. It's not as straightforward, or more accurately, it's a function of J0 and theta. More to the point, one can specify for each DMU J0 in a faculty a type of parametric production possibility set. Next slide. Turning to the university example, the essential difference between the application of Model 3 versus the conventional model is that in the conventional model, when you do the data envelopment analysis exercise, the only positive lambdas that you get are those that lie on the frontier. So whenever you project something to the frontier, it's only those DMUs that constitute the peers. In the case of a shared input, however, this is no longer the situation. If you look at this simple excerpt from the results for Model 3, I've chosen faculty 5, which has 3 departments within it. They're designated as departments 12, 13, 14, 15, and 16. Notice that departments 13 and 16 are efficient. And also notice that DMU number 12 is inefficient with an efficiency score of 0.6. So also is DMU 14, 15. Let's look at DMU 14. When we set out to find the efficiency of DMU number 14, notice what the lambdas are. Lambda 12, lambda 16, and in the end, lambda 32. Right. And all other lambdas are 0. However, the interesting point here is that DMU number 12 is not on the frontier. It's an inefficient point. So what happens in this case is that what is happening is that there are two types of DMUs here, namely those that are fixed and those that are altered during the optimization process. Since the efficiency score for DMU number 12 is larger than that for DMU 14, the former, number 12, will be closer to the frontier as defined by theta than is the case for DMU 14. So DMU 12 gets to the frontier before DMU 14 arrives. The important point to be made here is that in evaluating DMU 14, it's not the shared input, xi plus 112, for DMU number 12 that is a peer for 14. Rather, it is the altered version of that shared input, namely theta xi plus 112, that acts as a peer for 14. So it's a quite different situation, much more complex, and probably deserves some further research. And next slide, and that's it. So thanks very much for listening, and hope you have a nice day.